So there we go. So on the top of this barn here, we've got a truss right there for the roof. That's a common roof truss. And there's a little bit of a truss holding up that roof right there. Maybe a little bit more decorative than anything. There's a bit of a truss right there. So you run into these things fairly often. Here off in the distance, we've got a truss on a railroad bridge. Okay. So what we have here for trusses is their structures are made of long, thin members. Members are like beams, basically, joined into triangles. Okay, so that's what a truss is. The one important thing here is they have to be formed into triangles. So there's some real specific assumptions we make about trusses. So there's some more rough trusses and a little closer view of that bridge truss there. There's a truss on our greenhouse outside of this building, actually, here on campus. So you can see the triangles right there. All right. So these things show up lots of places. So what we do, we take long, thin structural members and join them into triangles. The members are joined only at their ends. Okay, so this would not be one separate or one long beam. That would be a series of shorter beams that have pin joints at their ends. Okay, so that's the assumption you make when you analyze a truss. So where the members come together are referred to as joints, and those are assumed to be pin joints there. Okay. Now, as a result of that way of making these, what you have for those members is you assume that they're what are called two-force members. We're assuming that we don't load the members any place other than the joints, and we join them only at the joints. Okay, so as a result, those members are what we call two-force members. Okay, so a two-force member is an object that has two pin joint supports and has forces applied only at the joints. So by itself, all a two-force member can do is resist an axial load. Okay? So they're like links. You know, we went over links a little bit when we were doing equilibrium. They're the same idea. So if I've got a member here and I apply, let's say I've got this member held vertically, but I'll apply loads to it at a 45-degree angle with my hands here, that's just going to pull off at 45. So the idea is the force goes from one joint to the other. That's the only force that a two-force member can support. Okay? So there's a two-force member. Notice the pin joints down there at the bottom. Long, thin member with pin joints top and bottom. No loads applied anywhere between the joints. Okay, there's a truss bridge that's crossing the Santiam River at Jefferson. Okay, you can see, it's kind of hard to see there, but you can see those pin joints that are joining those members together. So some of the old school bridges actually use pin joints. Nowadays they use gusset plates more, but there you see a good view of one of those pin joints holding that together. Okay.
What's a gusset plate?
What is a gusset plate?
Yeah.
A gusset plate is, well, let's get through a couple more pin joints. Here's our greenhouse truss. You can see pin joints there. Kind of a crude little joint there, but that's what they act as. They act like pin joints. A gusset plate is a plate like that has, in the old days they had quite a lot of rivets in them. They might have screws. You see them used on plywood where they have spikes. You know, they have like spike plates. I don't know what they call those things, but they're like gusset plates. They're plates that join members together. So those are how you connect bridges. There's a gusset plate right there. You see all the rivets punched through that. Yeah, lots of rivets. Okay. Okay, so there's some gusset plates right there with the joints. Okay. All right, now even if you have gusset plates, you can assume that acts a lot like a pin joint. If you extended that member out and applied a force as I'm showing to it, you could get that member to swing a little bit. If it's long and thin, even if it's pretty well held at one end, you could still get a little bit of sway out of it. So even though that isn't a perfect model, you can model that as a pin joint. It's not a perfect model, but it works well enough for our analysis. Okay. Okay, so on its own, a two-force member can only support an axial load. That's a load that is directed from one pin to the other. Okay, so notice if you have that two-force member, which I'm showing you here, if you push towards the other joint, that's fine. As long as that push is directly in line with the other joint, that's a stable support there. But if you push off the line, if you're not pushing towards the other joint, what this thing would start to do, it would start to rotate. So two-force members on their own are not stable when you apply a non-axial load. Okay? So they have to have axial loads in them. That's the only load they can support on their own. Now they can support a non-axial load if you put a second two-force member in there to help. But on its own, a two-force member cannot support a non-axial load. So the assumption we make if we build something out of two-force members is that all the loads are axial. So as a result, there's two types of loads that we can have. We can have compression, which pushes, or we can have tension that pulls. Okay? Those are both two types of axial loads. Okay? And those are the two options for these two-force members, compression or tension, one or the other. So they don't build up any shear, which means you can design them long and thin because they don't have to resist that shearing action. Okay? So that's a key assumption on this, is if the members that make up the truss are joined only at the joints, if the loads are applied only at the joints, the members are two-force members, and they're either in pure compression or pure tension, one or the other. Okay. So we good with that? Okay. All right, now when we analyze these things, we'll start by using what's called the method of joints. So we'll analyze each successive joint and see what it takes to hold it in equilibrium. Now, so keep in mind we're analyzing the joints. So here's a truss. So we use a series of arrows in there that might seem a little counterintuitive, but this member here is in compression because what we're showing is we're showing what it's doing to the joints. It's pushing on the joints, so the arrows show a push on the joints. This bottom member here would be in tension. It's pulling on the joints on page 480. Okay, so keep in mind that those arrows indicate what you're doing to the joints. Okay. Now there's also a nice little formula to determine if a truss is statically determinate or not. The members plus 3, m plus 3, should equal 2 times the number of joints. That's how you tell if a truss is statically determinate or not. Okay. If m plus 3 is less than 2 times the number of joints, there's too few members and the truss is unstable. If it's greater than 2j, there's too many members and you can't work it out with just statics. Okay? It'll be statically indeterminate then. All right. Now let's work through a truss here. Okay. And that'll start on the next page. So you always start off by finding the reactions on a truss. That's always how you start. And what I mean by that is you treat the truss as one whole object. So I'll just outline it in red. Think of this as just being like a plate, a trapezoidal shaped plate. And then we're applying these 3 loads to it. And we want to find the reactions at the 2 supports, the pin joint and the roller. So we want to find that and that, okay? So to accomplish that, you would find the reactions. So take moments about A, you'll have the 8,000 times 1. That'll be clockwise, negative. 9,000 times 1 and 2 makes 3, negative. And 7,400 times 2, 2, and 1 makes 5. Counteracting that, you'll have 6 times the reaction at F. You can solve for the reaction at F, and that's 12,000 newtons. You can then sum forces in the y direction, solve for RAY, it's 12,400. Okay? So before you try and do a truss analysis, generally speaking, you want to find the reactions on the truss first. Okay? You always want to do that. So that's step number 1. Okay. Step number 2, are we good with that? Getting those reactions? We got any questions on that? Good? Okay. You also want to know the angles that the members make in the truss. You usually have X and Y dimensions for the members. Use those dimensions to come up with the angles of the members using arctangent. So we got 1.5 over 1. That'll get us those 56.31 degree angles for AB and EF. And then we've got 1.5 to 2, and that'll get us the angles for BD and DE right there, okay? So just do all the preliminary stuff. Get the reactions on the truss, find the angles that the members of the truss make. Okay. Now, once you got that stuff figured out, what you do is you start working your way through the joints. So now we're going to break the truss up into pieces, the members, and start solving for them. Okay? And we're going to use equations of equilibrium. We've got 2 of them that we can use on a joint, sum of fx and sum of fy. So we got 2 equations we can use for each joint. So we have to start at a joint that has a known force and only 2 unknowns, because I've only got 2 equations to work with, and I need a known force to get me some starting value, you know, that I could use to figure out what the other values are going to be. Okay, so what I decided to do there was to start at joint F. Okay. So what I'm doing there, I'm going to take joint F and I'm going to draw it. So there it is. Right there. And then I've got 2 members that come into F, and I'm going to replace the members with forces. Now those are axial forces, so the line of the member is the line of the force. So FDF, I'll assume is horizontal. I'm assuming that it's pushing on F. And FDF is at a 56.31 degree angle. So I'll assume that that's pushing on F at that angle. And then I have the upward force of the reaction. Okay. So that's my little free body diagram of F. So what I'm doing there is I'm cutting out joint F like that. And when I cut through those members, they become forces. In this case, I'm assuming they're both pushing on F. So if they're pushing, I'm assuming those members are in tension or compression. Compression, okay? And I show them pushing on the joint. So what I'm showing here is not what happens to the members. I'm showing what the members do to the joint. So keep that in mind. Compression pushes on joints, tension pulls on joints. All right. So when I look at that joint, what I'm going to notice is that DF is an X component only, EF has an X and a Y component. So it looks to me like I should start with a sum of forces in the Y because I'll only have one unknown, and that will be EF. So I got 12,000 up for the reaction minus sine of the angle, sine 56.31 times FEF. Okay. Can run through the numbers there. I'll take the sine 56.31, that's 0.8321 times FEF. Take that to this side of the equation, it becomes positive. Set it equal to the 12,000 and solve, and I'll get FEF is 14,422. My answer comes out positive, and that means that it's in compression, as I assumed. It's pushing down and to the right on the joint. Okay. So that's compression, 14,422. Okay. So once I've got that, I go to sum of Fx, set that equal to 0. I got FDF to the right, and as I have it drawn, plus cosine of the angle times the now known 14,422. So cosine 56.31 times 14,422. I'll solve for FDF, and that'll equal negative 8,000. Well, what that means is my assumption was wrong. DF doesn't push on the joint to the right, it pulls the joint to the left. Okay. So I'll reverse that arrow so that it's a pull. That means DF is 8,000 tension that pulls on the joint. Okay. Questions on that? Okay.
So you don't know if it's in tension or compression until you actually solve it?
Yeah, you can take a pretty good guess sometimes, but yeah, the proof is in the numbers. If you get a negative answer, it just means you guessed wrong. You just turn it around. No big deal. Okay. So what I found here is that that top arrow is good, but the bottom one isn't. It's actually pulling. And then I've got the magnitudes now, 14,422 and 8,000. And then the other thing is, now what I'm going to do is take those forces and those members and push them out to the other side. So if EF is pushing on E, or on F, excuse me, it's also pushing on E, okay? And if DE is pulling on, excuse me, if DF is pulling on F, it's also pulling on D. So you got to watch how those arrows go in, okay? If you think of DF as being like a rubber band and you think of pulling on it with both of your hands, it pulls both of your hands in, doesn't it? That's what tension is like, a rubber band that's being stretched. And if you think of EF like a block of foam rubber that you're pushing in with your hands, it pushes both of your hands out. It's in compression. So you want to remember to turn those arrows around, okay, when you go on the opposite side. So that's how you draw the arrows for what's happening with those members. Compression pushes on the joints, tension pulls on the joints. Okay. So we all right with that? All right. So, and once you get one, you just march off to the next one. You just work your way through the truss. Where should we go next, do you think? I would just, once I start in a place, I just start kind of working my way through. So E or D? Yeah, I think E is the place to go because all I see at E now is two unknowns because I've already found EF. But if I go to D, I've still got 1, 2, 3, 4 unknowns. I can't solve D out yet. I don't have enough known information yet. But I can go up to E, so that's where I'd go. Okay. So next I'll go up to E. You know, there's my free body diagram. Now, a few little things here. Remember to turn the forces around so that 442 is pushing on E. Remember to include the 7400 applied load at the top. And then you got CE and DE. Okay. And then you can do sum of Fy is 0. I'm going to start with that because I only have one Y unknown, and that's DE. Notice that CE is horizontal. It doesn't have a Y component. So what, I got 7400 down. I've got plus sine 56.31 times the 14422. And as I have it drawn, I've got minus sine 36.87 times FDE. That's 0.6 FDE. I bring that to the other side of the equation, work out the rest of the numbers. So 0.6 FDE is negative 7,400 plus 12,000. I can go ahead and solve for FDE. It's positive 7667. Positive meaning it is as assumed. Down left, it's tension. Okay. And then I got FCE to the right. I've got minus cosine 36.87 times the 7667, because that's going to the left. That's this one. I'll also have minus for that one, cosine 56.31 times the 14422. So FCE is 14,133 in the direction assumed. So it's going to the right. It's compression. And that's the basic process. You just work your way through the truss, just one step at a time. Remember, you find the reactions first, start at a joint with only two unknowns and a known force. And remember to turn the arrows around. And remember to include the applied forces as you work your way through. Okay. All right. Well, we go to joint C. We got the 14,133 to the left because that CE is in compression. I'll assume BC is in compression also, and that works out. It's the same thing as CE. It's 14,133 newtons compression. And then I can write up the equation for, in the Y direction, I get sum of Fy is 0 equals what? What's that? 9,000? Okay. Now, when you do analysis of a member, you do it with the joints. So what I'm looking at here is joint C. So I just work with that. I just draw that boundary around. And all I cut through there is CD. So what I'm going to get is 0 is equal to FCD. Now that 9,000 is not applied at joint C, it's applied at joint D. And see, that can get spread between any number of members at D. So you can't just take the 9,000 and even, I know that deal with the line of action, you can move it. You can't really do that with a truss. You have to apply it to the joint it's actually applied to. It's applied to joint D, not joint C. So what I'm getting there is sum of Fy is 0, and that's FCD. And that's really about all that's going on there. So FCD comes out to be 0. That's called a zero force member. Okay. So by looking at joint C, I can tell that that member isn't doing anything. It bears no load. It's just sitting there right now. I can tell that by looking at joint C. And these come up, so they even have a name. They're just called zero force members. Now why might that be in there?
It might have a load changes and changes under some circumstances it could have.
Yeah, there could be other loadings. When you're building it, you might need it. You know, it could be supporting certain things. I mean, there's different reasons why you might have these in there. But just keep in mind that some of these members can have a zero force in them. You can prove it at one joint. Now notice you would not see that CD is 0 if you look at joint D. It's way too complicated down there. But you can see it at joint C. Because it's the only thing with a Y component at C, it's not bearing any load there. Okay?
Does that still count as a member when you do the N+3 equals?
Yeah, it does. It counts in the... If you removed CD, you'd have to make BE one solid member. You know, if you were to change that truss around. So if you know what I mean, you know, there's a joint at C. If you remove CD, you'd have one solid member running across. Okay. All right. So that's a zero force member. Okay, those are kind of odd. All right. You two can do method of joints, so why don't you find the forces in BD and AD. And you've got a space there to do it. So just kind of work through the equilibrium on that. So you're at joint D is where you're at. Okay, so get a free body diagram of the joint first, and then sum of Fx and sum of Fy. Just approach that, you know, in a way that will get you to one equation with one unknown first, if you can do that.